Start? Okay, so let me start just with a brief recap of all the lectures. Today is the last lecture, so I'll see how much I can do. So, as I told you, the essential, sort of map work is that we started with, again, always remember that we have an n by n matrix, and it's rotationally invariant or Wigner matrices. So we have some probability distribution of the entries of this matrix, H. And so then we said, okay, for rotational invariant, so the main problem is to actually compute from this matrix distribution of entries to the joint distribution of eigenvalues, okay? So starting from this, compute this, okay? So that's the step number one. And that itself is very difficult, not always easy. And at least for rotational invariant ensembles, what we saw in the last class that you can actually derive this, and this is in general given by for Gaussian ensemble. There's a beta there. And then we sort of interpreted this as the Coulomb gas or the log gas of interacting particles, of n interacting particles. So these are on a line. They are sitting in this external harmonic potential, which is this term of the energy. And then each pair is repelling each other by a 2D log interaction, logarithmic Coulomb repulsion in 2D, which is a log interaction, okay? So once we have done this step, once we have this, so then it's reduced to a problem of statistical mechanics problems of 1D. So now we have a StatMech problem. But only unusual thing here is that there is a long-range interaction because of this pairwise repulsion, which is not the case usually when you look at the short-range Ising model. Okay, so this makes a fundamental difference to the StatMech system, and the usual techniques that you apply, for example, short-range Ising model, most of you have done the calculation in your masters or whatever later. You can use transfer matrix techniques and other techniques to calculate the partition function. But here, we cannot use those techniques because there is no concept of transfer matrix. It's not getting transferred from site to site. So it's actually long range, everybody is interacting with everybody. So solving, even starting from this to calculate several observables is not that always easy. So I defined a set of observables. These are interesting questions to ask. For example, average density of states, normalized to unity. So this is this rho n lambda bar, which is defined as averages with respect to this Gibbs measure. And then we looked at other things like correlation function. Didn't look, we defined. Then spacing distribution. Counting statistics, number of eigenvalues in this given interval. And then lastly, I discussed about the largest eigenvalue. Largest or smallest. So what we did in the last class, we defined these observables, and we discussed, why they are important, and then where are the motivations for studying such questions. So therefore, the problem now is actually reduced to a technical problem. You define the energy of this StatMech system, and you want to compute these guys. Okay. So now it's a sort of mathematical problem, if you like. That's how to compute different observables. And the techniques here are, as I said, are fundamentally different from short-range systems. Okay, so and not just techniques, but even the physics is quite different because, if you, for example, compute for Ising model, the free energy, which is just a log of the partition function, so how does it behave for large n? If you have a big system size, free energy is proportional to what? Yes? Just take a 1D Ising model or 2D Ising model, short range. Nearest neighbor. So how does the free energy behave with the system size? Linear, yes. So it's an extensive system. That means if you double the size of your system, free energy doubles, right? So you'll see that that's a consequence of short range problem. Okay. If you have long range system, your free energy or energy is not going to be extensive in n. It will be actually n squared. We'll see that in a minute. Okay. So this is the sort of problem that so we have to find out some new techniques. So there are two approaches I just mentioned first. Maybe okay. So there are two approaches. So one is what is called the finite n approach. That means you want to find some exact result for any finite n. Okay. Now this is, of course, very hard. Okay. So this is very hard. Except, as I mentioned several times, except for this special case of beta equal to 2, which is the GUE. You remember this beta was the power of the van der Monde determinant in this log interaction. And for beta equal to 2, when there is a van der Monde square, then you can write this as a determinant. And then a lot of simplification happens. And I just mentioned, but I didn't show you. So this is called the determinantal point process. And using this property of determinantal process, that you can actually calculate many things exactly. So many properties can be computed explicitly. Unfortunately, I won't have time to show you this. But you can go and read up the literature. At least you know the name now. Okay. So this is a very hard approach, except for this beta equal to 2 case and few other cases. But there's another approach, which is a directly large n asymptotic approach. So this approach is suited for large n already. Okay. So if you're interested in large n, essentially what you do you have lots of charges, and you can replace it by a continuum charge density, and you can do a field theory. Okay? So this is usually, people call it Coulomb gas approach, although it's a misnomer. I mean, Coulomb gas field theory. Okay? So many global quantities, like density of states and so on, you can actually compute it in a much simpler way using this approach. However, if you are interested in finer local properties, for example, if you are interested in what is the correlation between two neighboring eigenvalues, so then this large n cannot detect such small microscopic distances. So for that, you have to somehow use finite n approach. Okay? So large n is for global quantities, like for example, if I want to calculate the average density of states, the large n approach is much simpler. You can also compute by finite n for beta equal to 2, and then take the large n limit, and then you can compare with this result. But this is a much easier, more physics approach, basically, and this is a more maths approach, if you like. No, there is no lattice length here. It's a continuum, always in the continuum. Okay?
Then how is that?
You will see in a minute. Okay. So, and so some cases here, I mean, I don't have time to do this, but if you are interested in a particular application to cold atom, which I didn't have again time, but I mentioned in my first lecture, cold trapped fermions in harmonic potential. So it's a quantum mechanical problem. But this problem you can map exactly to the GUE problem, and then you can use the properties of GUE. So if you are interested in this approach, so I just cite a review and that we wrote recently, and you can read that, since I don't have time to talk about this. You can find this in the archive also. Okay, so I'm not going to talk about any more. So what I'll do in the rest of the lecture, I'll just focus on this field theory large n approach, because it's more physical, and at least I hope that we'll be able to compute this directly density of states and show that it has this weakness semicircular form. Okay, so that's the program of today. Okay, so this is the large n continuum approach. So before we proceed with this large n continuum approach, it's actually first good to estimate how what is the scaling, okay? So I have these charges, right? So there are two terms in energy, as I said. So there is a potential energy term that each charge is filling due to the external harmonic potential. And then there is this log repulsion, okay? So what is this typical scale of lambda? These two terms, I told you, they are competing with each other. These guys are trying to push the particles towards the center of the trap, whereas they are trying to repel each other. As a result, they will settle down over a finite region of space, and we want to sort of estimate what is this. This, of course, will depend on n, right? So how does it depend, the scale, for large n? Okay? So what is the typical scale? Of lambda. So let's estimate. So let's look at the first term first. Okay, so E1, which is the external energy term. This is just a heuristic this thing. So this will be, roughly speaking, there are n such terms. So this will be n times lambda typic square, right? I want to estimate this lambda typic. So the first term of the energy is scaling like n lambda tip square. Okay. What about the interaction term, second term? So this is just minus half log how many terms are there? Yes, every pair is interacting with every pair. So, NC2, n into n minus 1, right? Because you don't count separate, you don't, 1, 2 is the same as 2, 1. So it's actually n into n minus 1 terms, right? So for large n, this is of order n square. So there are order n square terms, okay? So therefore this term typically scales like n square, this energy, interaction energy, okay? Now, so in order that they compete with each other, so they should be of the same order, right? So if they are of the same order, then I should, equate this guy with n times lambda typic square. So 1n cancels. So what you have is this lambda typic scaling like square root of n. Okay? So if you just, generate, for example, numerically these charges on this according to this weight by Metropolis or whatever algorithm, you will see that typically they will scale like root n. Okay, root n times something. Okay, the scale is root n. So therefore, in order to derive a sort of large n limit, it's useful to rescale all the lambdas by the square root of n. Okay, so what I'll do, rescale that means lambda I goes to square root of n lambda I. Okay? Just make a change of variable because nothing else, it doesn't really matter, it's just a scale, but just to put them on the same footing essentially. Okay? So if I do that, then my joint distribution in this new rescaled variable, okay, I'm not writing everything explicitly, but so lambda is square, so this will be, so once you rescale, so this will be beta n times lambda is square by 2. Now when you rescale this term, if you replace lambda I by square root of n lambda I, of course there will be, so this will be square root of n times lambda I minus lambda j. So there's the overall half log n will go out. Okay. But this overall half log n is just a constant term which you can absorb in the normalization constant, right? So effectively this term remains the same. Okay? Yeah.
In that argument there, spoke about the interaction.
Right.
Should it be n square non-lambda?
No, this is the order of magnitude estimate. Okay, because log of lambda, if you rescale lambda by a thing, it just gives rise to a constant, right? That's what exactly I'm showing you. So this extra term doesn't matter. So log lambda is of order 1 number. Okay. This is the order of magnitude estimate scale. Okay. Yeah. Don't take this equation, I'm not equating, order of magnitude evaluation, yes.
Right. But so what, are we assuming that these two terms will continue to compete in the large?
Yes.
Are we assuming?
Not assuming, I mean, this is what happens, okay.
Like
how do you know? I mean, you just do it and then see. See what happens, no, I mean, this is, otherwise, you will get a completely trivial theory. I mean, you see, these things, I mean, think of this log interaction is just an outside factor, right? Overall outside factor and the Gaussian. So they have to, in order to, produce any sort of physical behavior, they have to. Otherwise, if the log term, if the interaction term was not important at all, then you will just get independent random variables. That's, you see that they're strongly correlating, right? So, okay, so you have this. So here, after this rescaling, so now all the lambdas are of order 1, okay? So basically, the whole idea of rescaling is that the eigenvalues, you have made it of order 1. So alternatively, you could have start from the matrix and you could choose your matrix elements, the variance to be of order 1 over n, and that would produce the same thing. Then you don't need to do the rescaling, okay? So, okay, so this is the starting point. And so then, so our partition function is just a multiple integral. So again, all the constant term I've absorbed in this. So this is the new partition function of this lambda of order 1 variables. Okay? So this is what you have to evaluate, this partition function for large n. Okay? Now, already you have seen that the energy, that means whatever is there, right? Beta times energy. So this energy is of order n square now. Okay? Because there's an n and these are all order 1, so there'll be n, and here also there are n into n minus 1 terms. So what you see that the energy of a configuration already of order n squared. Already this is different from the short range systems, because short range systems like Ising model, nearest neighbor Ising model, the energy is of order n. If you have n sides of your lattice, it will be order n, okay? But here, it's already order n squared. And this is a hallmark of long range systems, okay? Because they all compete with each other. So it's a non-extensive system. So to deal with such systems, we have to do something else. So how do you do the field theory for this? Okay. So when you do field theory, meaning that you want to write a continuum theory, so what you have a discrete set of charges, right, on a line. N is very large, so they are quite dense. You have a dense set of points on the line. But they are not uniform. There are fluctuations, there are variables, basically. So the idea when you want to go to the continuum limit, like always you do, if you have a large number of points, what's a good description? Instead of saying this point is here, this point is there, this point is there, this point is there, how do you actually describe a system? For example, water. If you have a liquid, for instance, okay. You're not going to say that my molecule number 1 is at this point, molecule number 2 is at that point, molecule number 3 is that point. You describe it in terms of some density, right? Some local density, which may vary from one point to another point, but it's a density. When you say density, what we mean is that it's like a small volume, and you actually, you coarse grain the system. That means locally, you just count, how many molecules are there in a small volume, and you call it local density, basically. Okay. So for large n, you do a coarse graining in the system. So how do you do the coarse graining? So the appropriate way to do this coarse graining is to, first you introduce, so step 1, I'll do step by step. So introduce and so-called empirical density. I'll tell you what this means. So this is just, what I was defining, that is, this object just gives you the local fraction of charges between lambda and lambda plus d lambda. I've not averaged over yet, okay? So this, of course, for finite n You see, it's a bunch of delta functions, right? It's sort of like these peaked delta functions, okay? As a function of lambda, which are peaked at lambda 1, lambda 2, lambda 3, lambda 4, etc. So what happens when n becomes very large, that they come closer to each other, and this sort of becomes a smooth function, okay? So this is in the large n limit. This guy approaches to a smooth function. That's an assumption. Of course, we are not proving this, but as a physicist, you would accept it. And of course, by definition, this guy is normalized to 1, right? Because you have n charges, if you integrate, you will get 1. So next point is important, which is that if I take any function and I do this sum, so this is exactly n times can you see that? Because you just use the definition, okay? So n times rho n lambda is sum over delta function. So this is, you see that if I substitute this formula here, this just becomes sum over delta lambda minus lambda I. And which is exactly summation I equal to 1 to fi, okay? So this relation, we are going to use this, so this is important. For any function, this is true. Okay, so this is the preamble, step 1 first. You have defined a density, okay? So now step 2, so step 2 is this coarse graining. So what does coarse graining mean? So this means there are two things. So it's a partial trace. I'll tell you what it means, partial tracing. So this is what statistical mechanics teaches you. Sum over all microscopic configurations of particles positions consistent. So you first fix the density, okay? So you have these charges, right? So imagine that I make little boxes here, like this. And I specify the local density. That means I specify how many particles are there in this little box, how many particles are there in this little box, how many particles are there in this little box, and so on. So this N1, N2, N3, this is roughly giving me the density profile, the macroscopic density profile. Now, given this density profile, that is, it's a given one specific density profile, and so consistent with this density profile, so you first fix the density, okay, N1, N2, N3, etc., and then you sum over all microscopic. So once you fix this N1, N2, N3, etc., you see you can move around these particle positions inside each box, right? It doesn't change this density here, okay? So you have some freedom, and so you have to sum over all such microscopic configurations. This is the thing that gives rise to entropy in statistical physics, right? And then, finally, you sum over all possible density profiles. This is the main idea behind anything, I mean, like density functional theory also, and so on, consistent with the constraint that they are normalized to 1. Okay, so the idea is clear, right? So I first, fix a macroscopic density, which I call rho n of lambda, which is a smooth function, and then I sum over all possible microscopic degrees of freedom which give rise to this macroscopic density, okay? So this is sort of hydrodynamics, basically. And so there's two steps. So I fix the density, I sum over all microscopic configurations, and then finally, I sum over all possible density profiles, okay? So what that means, therefore, then I can do this integral here, which is a n-fold multiple integral in two steps. Okay, I'll first write down, and then you'll see immediately. So this is the second step, summing over all possible density profiles, and this D means functional integral. That means you think of all possible functions here, okay? And all these functions, they have to satisfy their normalization constant, so there's a delta function, okay? And then I have e to the power minus beta, okay? So now, look at this guy here, okay? So this sum, lambda I square, I can use this formula here to replace the So this double sum, I've just replaced, again using the same formula, by a double integral, okay? So you just locally, just think of this as a discrete sum you replace by an integral. And because of this multiplied by n, so there's a factor n squared that comes from each factor, and it goes outside the sum here. Okay, so when you do this, of course, you have to be a little bit careful, because you see that you cannot put lambda I equal to lambda j, because then it sort of diverges, right? So there's an implicit cutoff here, that is, two particles can never come on top of each other, but there'll be some kind of cutoff here, okay? So you have to think of some epsilon cutoff or delta cutoff, essentially, okay? So log is not very close to each other. And so that will give rise to an extra term, and you can show, okay, I'll not spend too much time on this, but you can show that this extra term, you can again express in terms of the density is like this. So this is usually called the self-energy term, okay? It's very easy to see how it comes about, because you see, essentially, this term here will be beta by 2. So when I is very close to j, I have only one summation. So this will be log of delta. Okay? But this delta is a local cutoff, is a local density, right? So local interparticle spacing. So this will be like 1 over the local density, basically. Okay? So then you take minus log lambda I and use this same formula here, and then you get this term n rho n lambda log n lambda. Okay? So, okay, and then what we have, so this is the energy term, right? So let me put this thing here. And then finally, I have to sum over, so what I'm left with is this integrals here. I'll explain in a minute. Okay. So remember that this is our definition of density, right? So I fix the density, which means that all microscopic configurations must satisfy this condition. So there's a delta function. Then I have to sum over all possible configurations. And there's the energy term, which involved lambda i's. But when I'm expressed in terms of the density, it just comes out of this multiple integral. Okay, so it just becomes this, and then there's the extra self-energy term. Okay. So these are the two steps, right? So the second step is this one, that is I integrate over all possible functionals, satisfying this constraint that it should be normalized to 1. Then there's the energy function, but the energy function comes out of the multiple integral once I fix the density. Energy can be expressed solely in terms of the density. That's the key point. Okay? So it goes outside this multiple integral. And what you're left with is just how many configurations of microscopic configurations are there consistent with this density. That's what this delta function means. So this is, you are familiar, I mean, this is what gives rise to the entropy term in statistical physics. So how do we estimate this entropy term? I want to do this integral here and express it in terms of density. So this is a very easy way, because how many ways can I put n parts? So I have n particles. How many ways can I put? So this is the estimation of the entropy term. How many ways can I put n particles into different boxes with n1 particles, n2 particles, etc. Right? So let's say you have m boxes. So you have divided your particle system into m boxes, and you put n1 particles in the first box, n2 particles in the second box, nm particles in the mth box. So this is just the number of ways you can put them, right? So it's all microscopic configurations. Okay? This is just a multinomial. So this we are going to estimate now. So this will be n factorial. N1, what is N1? N1 is just n times the local density. So this is rho n at lambda 1, okay, around lambda 1, let's say. And then the N2, which is number of particles in the second box, so that will be n times the local density there, and so on. Right? So then you use the Stirling approximation, because you are in the large n limit. Which says that L factorial goes like for large L, log L minus L. Okay? So here, each term has an n in it, density is of order 1. So therefore, I can just use Stirling formula for everything. And okay, this I'll leave you to exercise. If you do this, what you will find that in the large n limit, using Stirling formula, this just becomes e to the power minus n, and then you have this sum over I, this all these guys basically. This is integral. Then you replace the sum by integral. Okay. So this is the famous mean field entropy. You have seen this formula somewhere, rho log n, log log rho. Okay. So therefore, what we are saying is that this guy here is approximated by this term, e to the power minus n rho n lambda log rho n lambda. Okay? Yes? Yeah, that's why I wrote n into rho n lambda. Rho n lambda is order 1. There's a factor n there. This is like exactly when we do binomial approximation. Binomial distribution, if you just for two things. Okay? So how do you show binomial going to Gaussian? You have to set m to be some order 1 number times n, and n minus m then just becomes 1 minus cn. You put this here, n factorial by cn factorial, and 1 minus cn factorial. And then you apply Stirling formula, because you can now apply Stirling formula to each term, because each of them is order n. C is of order 1. Okay? The same idea here. Because your local density is fixed, order 1 quantity, and you just take the large n limit. So it's very simple actually. So therefore, this term gives rise to the entropy, and what you see that the entropy term, which is e to the power, because you know how many ways, I mean, you know from your statistical mechanics course that entropy means how many ways can you, how many microscopic states correspond to given macroscopic state, right? And we usually write this as e to the power entropy. This is just the number of possible ways consistent with the given macroscopic state. So this is what is called entropy. So therefore entropy is this term here, and log of density, this is a fraction, remember, so the log of something is negative, so therefore entropy is a positive term. So entropy is therefore just minus n times so what you see, first difference from the standard short range system is that you see the energy here, energy is of order n square, but the entropy term is of order n. Okay? In the usual StatMech system, both energy and entropy both are of order n, both are extensive. Okay? But in this long range system, energy dominates compared to entropy. Okay? So we can basically, in the large n limit, we can drop the entropy term. Okay, well, let me first write down this cleanly. We have a functional integral and then there is this self-energy term, and there is this entropy term, okay? So what you get, the next order correction term is actually then there will be other, lower order corrections term because we are coarse graining, so there will be other, correction terms and so on. But you see the self-energy and the entropy, they are both of the same order, and they're of order n. Whereas the energy term here is order n square. And whole idea of rescaling is that you explicitly see that this n square is coming out, and this is an order 1 quantity, and then n order 1 quantity, and so on. Okay? So therefore, in this long range system, I can, to a leading order approximation for large n, I can neglect the entropy and self-energy term. Okay? So what I'm left with then is just one single functional integral. Okay, so finally, therefore, in the large n limit, we have then approximate formula here, which says this is a functional integral over all possible densities, and it has this energy term here. Okay, this n I'm just keeping it here, but you will see that large n limit, the density, of course, becomes independent of n. So let me drop it here. You can show that. Okay, we'll see that in a minute. Okay, I've dropped the entropy term. So in the end, eventually, this is just, I'm just saying, if you look at this, all you have done is effectively replaced this sum by an integrals, okay? But we did all these things to show that indeed the entropy term doesn't contribute, okay? As long as beta is the order 1. And then you have this extra constraint that not all densities are allowed. The density has to be positive, and it has to satisfy the normalization condition. You cannot just choose any arbitrary function, right? This function is is a fraction of charges, so therefore it must satisfy this constraint that it's normalization. Okay. So the next step is to actually sort of replace this. You want to somehow get rid of the delta function. How do you get rid of delta function? So if you have something, one way to nicely replace delta function is to use the integral representation. Right? Where this k is going from minus infinity to plus infinity. Alternatively, you can write this as ds over 2 pi I, just put k equal to si, and then it's minus I infinity to plus I infinity e to the power s x minus a. So it's like you are going in the complex plane in the perpendicular direction, doesn't matter. So the idea is that you can use the delta function in the integral representation and raise this guy up in the exponent. Okay. So in fact, so what we'll do, we'll use this, and this 2 pi, etc. It's not important, but s into so you see this s, therefore, so you have now a functional integral, and you will have one more integral over this s variable, and then this s just enforces this constraint. Okay, so this is what people in classical books, I mean, when you read first, they tell you this is as a Lagrange multiplier, right? Lagrange multiplier is nothing but replacing a delta function by its integral representation. Okay, so this is just Lagrange multiplier, and now we want to, of course, rescale because this constraint is important. So therefore, you can actually rescale again s to s times n square in order that this is of the same term as this. Okay, so if you do that, then finally what you get is something like this. I call it mu times n square. Let's say mu 0 times n square. So what you get is, so this integral, I'm not keeping track of factors outside, so it's not really important. Into some action here, which depends on this rho lambda and this mu 0. And this action, which is energy basically, is just that guy over there, lambda square rho lambda d lambda minus rho lambda prime log and then you have this constraint, which is, let me use this notation here, plus mu naught. Okay, so this is the, we have a field theory now with a given action, which is essentially only has energy term and no entropy term. And the energy is, there is this external potential, and there is this, and this whole method, of course, you can do beyond the Gaussian case, is just the lambda square gets replaced by V of lambda for general potential, matrix potential. Okay? So you see explicitly that this is exactly the Lagrange multiplier. I mean, this is what you do usually when you have a if you have to minimize some problem with respect to some constraint. I mean, this is exactly what you do. You have a Lagrange multiplier which, just enforces the constraint. Okay. So now, what you see here is you have a situation here where there's an explicit n which is coming over here, right? So that immediately tells you whenever you have an integral where you have a e to the power minus some power of n times something. So this tells you that there's a way to estimate such integrals, which is what is called the method of steepest descent or saddle point method. So all that says that this integral here effectively for large n, see large n, so the minimum of this guy, so you look at all possible densities and mu naught, and that one which has the lowest amount of energy or action, that's what is going to contribute, because all the other terms which are higher than that, they will be very, very, very tiny, small, okay? So therefore, saddle point approximation density, you just replace it, this integral, by its saddle point value, which is, S of rho star of lambda, mu naught star, I will call it mu naught. Where this rho star lambda and mu naught star are such that you have to make it a minimum. That means you have to take the functional derivative with respect to rho lambda equal to 0. So take derivative and solve for rho lambda, and that will give you the rho star of lambda, the saddle point value. And also you have to satisfy because this is a two-dimensional thing, right? You have to find out the mu naught also. So this has to be 0. But when you do del S del mu naught equal to 0, you just get back the constraint. Okay, so it's nothing. So you just have to look for solutions of this saddle point, okay, which satisfy this normalization condition. Okay. So this is the saddle point method. So this will also give us an estimate for the partition function. How does it behave for large n? Somebody was asking me the other day, but you see that it actually, goes like e to the power minus n square. So this is the main thing, and because energy is about n square. Okay, so let's take the derivative with respect to rho lambda. So we want to find out what is the saddle point density. And the other thing is that once you have this large n limit, so now if you want to calculate, for instance, this is the partition function, but if you want to calculate the average density of states, all you have to do is to just plug in here the density definition, that is the rho of lambda, basically, okay. So average density so this will be I will stick in the definition of density basically, okay. So delta of rho n lambda, okay. What I'm trying to point out is that for large n, what happens is that the saddle point density itself will also be the average density, okay. So saddle point density, because everything is controlled by the saddle point, so you have to make any stat-make average. If you do, only the saddle point will contribute to any average quantity. So saddle point density itself is also the average density for large n. Okay, so let's take a functional derivative of that. So del S del rho lambda gives me what? Tell me. I want to evaluate this. What's the first term from here? Think of a discrete sum. So if you take a derivative with respect to rho of lambda, it gives you lambda square, right? And the second term will give me, I'm taking functional derivative with respect to rho of lambda. So second term should give me this. And there's a factor 2 because it could be from this or from that, right? I'm just taking functional derivative with respect to rho lambda. And then have a plus mu naught equal to 0. Yeah? Very good question. Yes, if you try to do that, it's very hard usually. Okay, but usually, what you would expect from physics is that it will be a saddle point effectively. Okay, but you are right, absolutely. You have to ensure that the Hessian matrix, determinant of the Hessian matrix, is essentially, I mean, if you want to find it, if this has to be minimum, I mean, it's a saddle point, then you have to find out the eigenvalues of the Hessian matrix and ensure that indeed it's a saddle point. Okay, but to prove all these things, already you'll see that this is quite complicated. Okay, to prove the saddle point, all these things, the philosophy is that okay, you find this, if there is a physical solution that you find eventually of the saddle point, then you are more or less ensured that there is this second derivative must be that way. Otherwise, you wouldn't get this. Okay. All right. For some reason, okay, I have in my note. Yeah, no, this is fine. Okay. Okay. So therefore, what we have is, you see, this is lambda square plus mu naught equal to 2. Okay, divide by 2. After all this, what you have done, you see this, and this is quite instructive to do this. What is this object here? Okay. So this is just the, I mean, imagine that you have a charge, okay? So this charge is in this Coulomb potential, okay? This test charge. So therefore, this is the sort of potential energy felt by the charge, okay? Minus of that. And so this is just the, if you take it on the other side, I mean, what I mean is this. So what this says is that if you take this external test charge, so this test charge is filling this external potential and also the electrostatic force from the other charges, which is repulsive interaction from the other charges. So this is the total energy felt by your test charge, okay? And what it says is that this total energy is actually conserved. I mean, it's a constant. It doesn't depend on where you put this charge, okay? So just bring in a test charge into this system, and you can put it anywhere, and it always feels the same energy, same total energy. It's conserved. It's independent of lambda, okay? And so first thing you notice is that this integral here, okay? So let's look at what are the anticipated behavior. If I go very far away at very large lambda, okay? So this guy goes like lambda square, and if this integral was also going, if it was valid, if this equation is valid everywhere, on the real line, then you have a problem, because you see, if I go very far away, let's say to positive lambda, infinity, then this guy going like lambda square, whereas this fellow here is going like log lambda. So this is much smaller compared to that. It can never compete with that guy. So how can you have a constant here? Okay? So this first thing that indicates that you do not, this equation cannot be valid over all lambda plane. That means it's valid where this rho is non-zero. It just indicates that the charge density must be over a finite support. Somewhere there. So this equation will be valid only in this regime. So I don't have the right to take the lambda going to infinity limit. Because had the support been infinite, then I would have a problem. I can never satisfy this equation. Okay? So the first thing that indicates, tells you that that there is a finite support. Okay? We do not know what the A and B are for the moment, but we know it has to be over a finite support. Okay? And we also think it's only one support. It could have been multiple supports, but let's assume for simplicity that it's one support. Okay. And so then this equation will be valid only for lambda between B and A. So now we have to solve this equation. So what you can do, you can take one more derivative of this equation with respect to lambda inside this support. I take any point here, where this equation is valid. I can take one more derivative. So if I take one more derivative, I'll get lambda. So the mu naught, this reason I'm taking the derivative, I want to get rid of this mu naught, right? So if I take the derivative, then you are come with this but this is of course nonsense because I just told you that this lambda has to be between A and B. So that means suppose you take this point lambda, okay? So this is going to diverge when lambda prime is coming to lambda, right? So therefore this integral has to be interpreted in the principal value sense. Okay? So you have to evaluate this integral as a principal value. Okay? That means you just evaluate like this and evict this point and go around it and just, so basically this part plus that part. You have to evict that point. So this is a very nice equation, and what it tells you is, so now our problem is that, so in general, so I mean if you have, instead of lambda square, if you have v of lambda, then here once you have taken the derivative, this should be v prime of lambda by 2, right? More general case. So our problem is to actually, you have given me the potential, external potential if you like, and I want to find the charge density that corresponds to this potential. So in some sense, this is inverse of electrostatic problem. In the usual electrostatic problem, you give me the charge density and I try to find out the potential, right? Here it's the inverse problem. Given the source function, so this I'll call in general some g of lambda. So g of lambda equal to lambda is our problem basically for a Gaussian case. So given g of lambda, invert this equation, which is a complicated equation, it's a principal value equation. So such equations are usually called the Cauchy singular value equations. Or sometimes it's called the Hilbert transform also. So this is the problem. Mathematical problem, technical problem now is that you've given me this. I want to solve this integral equation. I want to find out what is rho lambda. Okay, and so if you look at standard book in random matrix theory, like Mehta's book, for example, you will find that he actually puts in the semicircular form on the right hand side and evaluates this integral and finds that the left hand side is equal to lambda, and therefore he says that okay, I mean this is the solution. Okay, but actually it turns out that many physicists for a long time they didn't know that such equations actually you can solve it exactly. There's an explicit solution of inversion formula due to an Italian mathematician called Tricomi. So the reason I wanted to do all this in detail is that now, if you have any long-range system, doesn't have to be, random matrix theory, you know how to do the field theory. You have to do the effective Coarse graining and write a density functional theory and try to find saddle point solutions of this. It's a very general method. Okay, so the explicit solution, so you have in general, so suppose you have an equation like that. So I want to find out what is the inversion formula. So this is FG Tricomi. So some mathematicians, like applied mathematicians, knew about this formula, but people working in random matrix theory, before we started working on it, they didn't know about this formula. So we somehow discovered it by accident, but it was extremely useful, this formula, for many, many calculations actually in random matrix theory. So this formula says that the rho of lambda, inversion formula, is exactly given by this result here. So imagine that it's supported over A and B. Of course, in our case, we still do not know what the support is. So this is the inversion formula. Okay, so B minus A, lambda minus A. So the source function, this is something that you know. So that goes in here. So you still have to evaluate this principal value integral plus an arbitrary constant. So now if you take the matrix potential to be any arbitrary V of lambda, then the source function, as you saw, this is V prime lambda prime over 2. That will come in here. And in general, for arbitrary potential to calculate the density is not so easy because you cannot do this integral. Okay? But if you take simple ones, like Gaussian case, where, so this is just lambda prime for Gaussian, or if you take a simple polynomial things, then you can actually perform this integral explicitly. So for instance, so let me just just give you some examples. This you can do it by hand. I mean, essentially you can do by Mathematica. So for instance, if you look at this guy, you should try this. Just to give you an example of such integrals. So this, for example, is very simple. This is pi by 2 lambda minus a plus b. So check this. Yes, just use Mathematica if you want, or do it by hand. And another formula that we'll need because this is exactly what we need. Because in our case, Gaussian case, g of lambda was just lambda prime, right? So we just need this integral. And this also you can do it explicitly. And this is just minus pi by 8 b minus a square minus 8 lambda square. You can do any polynomial, you can actually do this explicitly. But we know you just need this formula here, okay? So then you have explicit solution. So you have, essentially if you look at this guy, so you'll have rho of lambda, we'll have three unknowns now, right? B, A, and this C0. But you have some conditions. What are the conditions? So one condition is that the rho of lambda, d lambda, must be normalized to 1. Okay, so that gives me one condition. The second condition, can anybody guess? Physics is all about symmetry. So you have this, you would guess that rho lambda equal to rho of minus lambda, right? Because as I said, this energy has a lambda to minus lambda symmetry, right? So clearly, if you put, lambda, change lambda to minus lambda, and you just change lambda prime to, other variable, then it should be invariant under that. So rho of lambda must be a symmetric function. And the third condition is that you don't expect, this is the potential like that, and they're repelling. So you'd expect charge density to something like that. It should vanish beyond a certain distance, right? It cannot diverge at A and B because, your potential is like this, so the density has to stop. It cannot go very far, right? So which means that rho lambda equal to rho minus lambda, which means that this support, which are A to B, so A must be equal to minus B, okay? And it says that rho at B and also at A, therefore, must vanish. Okay? So you have 3 unknowns and 3 constants. So you put in this equation, and what you get is the famous, so this is your saddle point density, rho star lambda. Very simple formula. So this is for lambda between square root of 2 minus square root of 2. Okay. So this is what is called the famous Wigner's semicircular law. So there are many different ways of deriving this result. Wigner certainly didn't derive it this way. But this is sort of probably, one of the simplest ones, because this method is actually very useful if you want to do, for example, calculate other objects, like for example, if you want to calculate some functionals of these eigenvalues or linear statistics or something, you can again use the field theory and, just find out the saddle point density, and so you can actually obtain explicit solution, okay? So therefore, what we have is Wigner's semicircular law. So the density, therefore, average density on normalized to 1 is lying between minus root 2 to plus root 2. So you plot this, so it's semicircle because it has a semicircular form. And so it says we have rescaled all the eigenvalues, so there's no n dependence anymore. So this is already, so what it says is that large n limit, your density of states now is independent of n. It's lying on a finite support from minus root 2 to plus root 2. So all the eigenvalues are here inside this. There are more eigenvalues near the center because the density is high, and less eigenvalues near the edges because the density is low, okay? So we can easily estimate, given this, what is the interparticle spacing scale of. I mean, this says the global density is independent of n, but the interparticle spacing clearly still depends on n because you are putting n particles in a finite region over space. We'll see that there are 2 scales here, okay? And this is very important in random matrix theory. So 2 scales. So one is called the bulk. So bulk means that you are looking deep inside this semicircular C, just right here on this thing. So here, this is very dense, the particles are densely packed, and you can ask, okay, what is the sort of, typical distance between this, so let's call it L bulk. What's the typical distance? Typical distance, I'm not talking about the distribution of that, just what's the scale of that, okay? So that scale is very simple because, it's just, you just have to, integrate your density over this, over this scale, let's say 0 to L, okay? So this should be essentially 1 over n, 0 to L bulk, right? Because if I go from one particle to the next particle, if I integrate the density, it's just density is just a fraction, right? So what fraction of particles are there? Because it's just the next particle, so therefore it's only one particle there. So it should be order 1 over n, right? And rho of lambda, for example, near the bulk here, rho of lambda is just a constant. Okay, so this is a constant of order 1. So effectively, if you do this integral, so therefore L bulk, okay, this is a constant, you don't care. So essentially it goes like order 1 over n. Okay? So that means near the trap center, the typical separation between the particles is of order 1 over n. Okay? What about the second scale, which is the edge? So edge means that you are looking, so here, you see this is very dense, but as you go closer to the edge, the typical separation between the particles increases. Okay? So this is the L edge. Because the density is small, that means fewer and fewer particles. So therefore, as you go towards root 2 and minus root 2 on symmetrical on the other side, the typical distance between the particles increases. So there is another scale here near the edge. And what is this scale? Edge. How can you estimate this? So again, this will bring back to what Joachim was saying today, Sanjib was saying, again to extreme value. And very simple argument if you do this density. So you see, so suppose this is the largest eigenvalue, right? So what this is saying is average density of states. So it also tells you, therefore, that lambda max average, largest eigenvalue, on an average, it's lying at square root of 2, plus some fluctuations. So we want to estimate this scale. So let's just again do the same thing. So I integrate, I go to the very edge of this spectrum, and I just, I integrate this density, rho lambda d lambda, from root 2 minus L edge till root 2, right? At the very edge, I'm just integrating the density and evaluating this area under this curve. So this, again, because this is the interparticle spacing, so this will be of order 1 over n, right? So we integrate the, remember this is a fraction. So when I integrate, this gives me the fraction of particles between this and that, which is 1 over n, because you are looking at the next particle. Okay? So now we have our semicircular law. So rho of lambda, which goes like square root of 2 minus lambda square. Okay, there's 1 over pi, but you don't care. This is order 1 over n. Okay. So of course, I can just make a change of variable here. So just call lambda equal to root 2 minus x. And x has to be small because here this is, both the limits are close to the lambda equal to root 2. So if you just, just do this, then you see that this will be just x to the power half, okay, up to some constant, dx, 0 to L edge, which will go like order 1 over n. So this means L edge to the power 3 over 2 goes like 1 over n. And therefore, L edge scales like order n to the power minus 2/3. Okay, so that means the spacing near this edge here, the typical interparticle spacing is order n to the power minus 2/3, whereas here, near the bulk, the typical interparticle spacing is of order 1 over n. Okay, so it already tells you that there is a scale which is very different at the edge than in the bulk, and so all activities of random matrix theory now, people try to understand both the properties of correlation functions, spacing distributions, etc., in the bulk and as well as at the edge. And because the fundamental length scales are different, so you would expect the properties of these eigenvalues, they will be very different in the bulk than in the edge. So for instance, I told you, sorry, this should not be average here. So what you expect there for lambda max, I talked about largest eigenvalue last class, so this should be on an average to root 2 plus some fluctuations, and we already guessed what the scale of, this is a random variable. So there will be n to the power minus 2/3 because I just told you that the scale typical fluctuations here. So if I look at the distribution of lambda max, it will be some distribution around its mean value, which is root 2, on a scale of order n to the power minus 2/3. So this should be n to the power minus 2/3 into some other random variable of order 1, okay? And this object, this random variable, so if you ask what is the probability distribution of this object z, so this is some function of z, and so this is what is the famous Tracy Widom distribution. Unfortunately, I don't have time to go into the details of Tracy Widom distribution, but just to tell you how the function looks like. It depends on this beta, of course. Tracy Widom distribution, you cannot calculate by this functional field theory method because this is very finer scale. You are probing the system on a scale of n to the power minus 2/3. Because when I'm doing this calculation here, I'm on a bigger bulk scale basically. So I cannot detect the small scale fluctuations that is there. And so for that you have to do a finite n computation that I mentioned. But unfortunately we don't have time to do that. I just want to tell you how does the Tracy Widom distribution looks like. So it's actually a solution of some complicated Ponlevy-2 equation, but it depends on beta. But it looks like if you plot, it almost looks like a Gaussian, okay? So I'm plotting f Tracy Widom, f beta of z. It depends on beta. It falls off faster here. It looks like Gaussian, but it's not quite Gaussian, okay? So in fact, the asymptotic properties of this guy here. So when z goes to plus infinity, it goes like exponential minus 2 beta by 3, z to the power 3 by 2, very different from Gaussian. And when z goes to minus infinity, it goes like exponential minus beta over 24 mod z cube. Okay? So it's very asymmetric distribution of lambda max. And then, just to finish it off, I mean, this Tracy Widom distribution, originally it was found computed by these two mathematicians, Craig Tracy and Harold Widom. In 1994, and for a while, nobody somehow paid much attention to this. Okay, it's just a one calculation. How does it matter? But then, starting from 1999 onwards, that people found many different systems, like for example, the so-called KPZ equation, Kardar-Parisi-Zhang equation of interface growth. It's a very different problem. It has nothing to do with random matrix per se. But if you look at the height distribution of the interface height in this Kardar-Parisi-Zhang model in 1+1 dimension, so it turns out that its height distribution is also given by Tracy Widom distribution. And then, people found, actually before even the KPZ, there was this random permutation problem. Again, I don't have time to go through all these details, but you can find in a few of the articles that I, cited in the course outline. And there are, plenty of popular articles also. I mean, there's an article by Natalie Olshover in the Quantum magazine. This is a popular article if you want to read. So there are many different systems and where people found this Tracy Widom distribution in liquid crystals, and now it has been measured in several experiments and so on. And so there's a lot of activity which is going on the distribution of lambda max. People try to compute the distribution of lambda max going, beyond the Gaussian ensemble. You can ask, okay, if I have some other potential, V of lambda, which is not Gaussian, how universal is this Tracy Widom distribution? Okay, so it turns out that no matter which potential you choose here, okay, as long as your density has this square root behavior at the edge, it's always given by Tracy Widom distribution. Okay, so this is the universality of Tracy Widom distribution. And also I mentioned about the Wigner matrices. So in the Wigner matrices also people have found that it's actually described by Tracy Widom distribution. So it's a very universal distribution, which appears in many different problems going even beyond random matrix theory. Okay, so there's a lot of excitement which is going on right now, but okay, we'll not have to talk about that. So I think okay, I sort of covered only 1/3 of what I prepared. So, but that's okay. But I hope that I've given you just a flavor of this field and what are the main questions and what are the interests, and so now you can go back and read the other articles and hopefully you will like it. Okay, so thank you very much.